Our next speaker is Dr. Uma Mahesh. Dr. Uma Mahesh is an associate professor at ATME College of Engineering in Mysore, India. He has served as an assistant professor, guest lecturer, and lecturer for 8.5 years. He has pursued his research in Vellore Institute of Technology, popularly known as WAIT in Chennai, and he has qualified UGC NET exam in December 2019. He obtained his master's degree, M.Tech in VLSI Design and Embedded Systems from VTU Karnataka, India in 2012, and bachelor's degree BE in Electronics and Communication Engineering from Visvesvaraya Technological University, popularly known as VTU, Karnataka, India in 2009. He is a member of the Optical Society of America. His current research interests are in the areas of digital holography, artificial intelligence, and machine learning. Please join me in welcoming our keynote speaker, Dr. Uma Mahesh.
Thank you very much, sir. Can I share my presentation, sir?
Yes, you can, Dr. Uma.
Thank you, sir. One minute. Good afternoon, everyone, as per Indian Standard Time. Uh, Myself, Dr. Uma Mahesh RN. So today I am going to give the talk about the topic on deep convolutional neural network for binary regression of three-dimensional objects using information retrieved from digital Fresnel holograms. This is one of my research articles in PhD. This has been published in Applied Physics B, Springer Journal. So this is the outline of my presentation. I will first give an idea about digital holography, deep learning, what is the 3D object I have used, and what is the hologram I have recorded, and what neural network I have used, and what are the results and conclusion. So first of all, what is holography? So first of all, whenever we consider a three-dimensional object, for example, an object which contains amplitude and phase information, when we capture the image of a three-dimensional object through a normal camera or a square law detector, we will get only intensity information. So the phase information will get lost. So if the 3D object information is O into e power I phi, O is the amplitude and phi is the phase. So when we capture the image from the camera, we will get the square of the information. So amplitude will be obtained and phase will get cancelled. So this is the major drawback of conventional imaging technique. So therefore we will go for holography. So in holography, we can capture both the intensity, that is the square of the amplitude, as well as the phase information. So in holography, what we will do, when we consider the 3D object, this object wave will be superimposed on the another plane wave, that is a reference wave. So here O into e power I phi represents the amplitude and phase information of object wave. R into e power I delta represents the amplitude and phase information of the reference wave. So what we do here is the object wave will be superimposed on the reference wave and we capture the image in such a way that it includes both object wave information as well as reference wave information. So what happens if I do like this? Phase will not get cancelled. So in this manner, I can get both intensity as well as phase of the object wave using this superposition principle. So this is called holographic principle. So as I told you in holography, we will use an object wave as well as a reference wave, and we will use both the waves in order to record the holographic image. So this is the actual working principle. We will consider a helium neon laser source, a coherent light source with a zero wavelength and a 0 degree phase angle that will be passed through the beam splitter. Beam splitter will separate the beam into two parts. 50% of the light beam will get scattered through the object and remaining 50% of the light beam gets scattered through the mirror. So this object beam and the reference beam gets interfered in order to form interference fringe pattern called hologram. If this interference fringe pattern is recorded by the photographic plate, then it is called conventional holography. Suppose if this hologram is recorded by the digital devices like charge coupled device or CMOS, complementary metal oxide semiconductor sensor, then it is called a digital hologram. So here we have used a digital holographic principle. O represents the object wave equation, R represents the reference wave equation, I represents the intensity of the recorded hologram, which contains the reference wave, object wave, as well as the square of the object wave, square of the reference wave, and the virtual image, that is the conjugate of the object wave. So in this manner, we will record the hologram, and this hologram will be passed through the numerical reconstruction algorithm. We have several algorithms like complex wave retrieval algorithm, amplitude complex wave retrieval algorithm, amplitude spectrum method, and several methods are there, convolution method. And using that algorithm, we will reconstruct the intensity image and the phase image. Next. So after applying the digital holography technique on the 3D object, we will apply deep learning. So deep learning is a branch of artificial intelligence which can be applied in several applications like classification, regression, reconstruction, segmentation, super resolution, unwrapping. In several applications, it can be applied. Next, we will use a 3D object construction, and we have constructed 18 3D objects. This is a real-time experiment where we have constructed circle, pentagon, circle, rectangle, circle, square, circle, triangle. One of the 3D objects I will tell you. For example, if I consider this XYZ coordinate, this is a three-dimensional coordinate where X coordinate represents the first plane, Y coordinate represents the second plane, and Z represents the distance or the depth between the first plane and the second plane. So if I consider a 3D object, a circle, pentagon, circle feature is present in the front plane, pentagon feature is present in the back plane. So in this manner, I will construct a 3D object, circle, pentagon. So if I do not use depth, then it is called a 2D object. Since I have used depth Z, it is called a 3D object. Next, after constructing these 3D objects, circle, pentagon, circle, rectangle, circle, triangle, circle, square, I have used digital holographic experimental setup. This is a real-time experiment where helium neon laser source has been used, which is passed through the spatial filter and further passed through the collimation lens and further passed through the beam splitter. So spatial filter will remove the unwanted interference patterns in the laser beam. Collimation beam will make the light beam parallel. This parallel light beam will be passed through the beam splitter, where 50% of the light beam is reflected through the mirror M1 and 50% of the light beam gets scattered through the 3D object. So this scattered 3D object, whatever the light beam gets reflected, it will form the object wave. So whatever the 3D objects we have constructed here, these 3D objects, pentagon, circle, rectangle, circle, square, circle, triangle, circle are used here, and we have recorded the hologram through the CMOS sensor. So we have used Fresnel propagation condition here. So this is the plane reference wave and this is the object wave. Object wave and reference wave gets interfered here, and which will be recorded through the CMOS sensor to form the hologram. We have recorded holograms at 15 distances. The wavelength of the helium neon laser source is 632 nanometer. Collimation lens focal length is 150 mm. CMOS sensor pixel pitch is 6 micron. The recorded hologram size is 1029 into 1029 because the camera size is 1600 into 1600. This is a real-time experiment which has been conducted in the lab. So after recording the hologram, we have formed the data set for 3 sets: training set, validation set, test set, where I have taken circle, triangle, circle, square, circle, pentagon, circle, rectangle in the first set and remaining 14 objects in the second set. Totally, we have taken 18 objects. Out of 18 objects, 4 objects are considered in set. Remaining 14 objects are considered in the second set. Why this is done like this? Because the problem I have considered is binary regression. Suppose if I have to perform multi-regression, then I would have considered multiple sets. Next, I have taken 75% for validation set, 15% for validation set, 75% for training set, 10% for test set. And I have formed the data set for 2268 concatenated intensity phase images. I have not used holograms. After recording hologram, this hologram is passed through the numerical reconstruction algorithm called complex wave retrieval method. And I have obtained both intensity and phase. and I have combined intensity and phase. This is the phase depth, this is the intensity, and by combining intensity and phase, this is called concatenated intensity phase image. So these are the training and validation images in the training set and validation set. Next, convolutional neural network. So after forming the data set for 2268 images, that data set is passed through the deep learning network to perform binary regression task. So convolutional neural network consists of feature extraction layer and classification layer. This classification layer is modified into regression layer to perform regression task. Only difference is in output layer, instead of doing classification, we will do regression, that is prediction between the two sets. We will consider single neuron and a linear activation function to produce the output. So the concatenated intensity phase image is of size 1029 into 3000, which will be reduced into 128 into 128 for the training purpose. I have taken 4 stages of convolutional layers and 4 stages of pooling layers. This is mainly dimensionality reduction, which will reduce the dimensionality of the feature map to produce the output. So in the first convolutional layer, I have taken 32 kernels. In the second convolutional layer, I have taken 64 kernels. In the last convolutional layer, I have taken 128 kernels. In the fourth convolutional layer, I have taken 256 kernels, where each kernel size is 3 cross 3. So I'll explain the convolutional layer working. So concatenated intensity phase image dataset is passed through this. Classification layer is modified into regression layer to perform the regression task and get the result. So in the convolutional layer, I have used rectified linear unit activation function. In the classification layer, it consists of fully connected layer as well as output layer. In the fully connected layer, I have used ReLU activation function. So what is this convolutional layer? Convolutional layer basically performs 2D convolution, where I have taken 6 cross 6 input multiplied with the 3 cross 3 kernel to produce a output of 4 cross 4. So here in the 6 cross 6 input, 3 cross 3 kernel is multiplied with the 3 cross 3. This is the input and this is the kernel size. 3 cross 3 matrix will be multiplied with the 3 cross 3 kernel to produce 1 pixel map in the output. So this output will be passed through the rectified linear unit activation function, and further it will be passed through the pooling layer. So in this manner, the convolution slides. First, it will take the first part of 3 cross 3. Next, it will take the second part of 3 cross 3. Next, it will take the next part of 3 cross 3. The same process repeats till the entire matrix is completed. So in this manner, we will do convolution. I have given 6 cross 6 input. I got 4 cross 4 output because my kernel size is 3 cross 3. So my output is n minus f plus 1. N is the input, f is the kernel, 1 is the bias. Bias is used to increase the performance of the neural network. So this is how convolutional layer works. This convolution output is passed through the rectified linear unit activation function. Rectified linear unit activation function considers the values for the right side of the x-axis and discards the values for the left side of the x-axis. So here, if you see x for x greater than 0, 0 for x less than 0. So this is the equation for the rectified linear unit activation function. Next, pooling layer. Pooling layer will further reduce the dimensionality of the feature map. Max pooling will perform maximum of the pixel value and it will get the result in the output. 1, 2, 2. Maximum pixel value is 3. 3, 4, 4, 5. Maximum pixel value is 5. We can also perform average pooling and sum pooling. This I have done in the program. So like this, we will do convolution and pooling operations successively for 4 stages in order to reduce the dimensionality of the feature map. So here you can see the model summary. The concatenated intensity phase image, I have considered the size is 128 into 128. And I have taken 3 cross 3 kernel. When I explained earlier, I had taken 6 cross 6 input. 6 cross 6 will multiplied with 3 cross 3 to get 4 cross 4. So 128 will be multiplied with 3 cross 3 to produce 126 cross 126. This 126 will be reduced to 63. 63 will be reduced to 61. 61 will be reduced to 30. 30 will be reduced to 28. So in this manner, convolution and pooling operation will be performed successively for 4 stages, and we will get the result in the 4th stage as 6 cross 6 cross 256, where I have taken 256 kernels in the fourth convolutional layer. Parameters will not affect in the pooling layer, whereas in the convolutional layer, parameters will get affected because we are performing mathematical operation. 64 kernels multiplied with 3 cross 3, multiplied with 32, multiplied with the size of the kernel is 3 cross 3, plus number of bias values is 64. That will give you the number of parameters. So why do we calculate the number of parameters? Parameters will decide the complexity of the neural network. If the parameters are more, the neural network is large. If the parameters are less, the neural network is small. Like that we will find out. And in the output layer, I have taken single neuron and linear activation function to produce the output. Now in the parameter 2, I have calculated the parameters. Similarly, in the parameter 1, 32 kernels are used. The size of the kernel is 3 cross 3 multiplied with 3 because there are 3 channels in the image, plus the number of bias values in accordance with the kernels, 32. Like this, I have done the calculation to find the number of parameters. So these are the parameter calculations I have done. In the final output layer, I have taken single neuron. 2048 neurons are selected. You can select n number of neurons. It's not a rule that I have to select 2048. Among 9216, this 2D vector is converted to 1D vector. In 9216, you can select 1000 also. You can select 100 also. So this will decide the parameters. Next, after calculating the parameters, we will proceed to the results and discussion section. You can see here, I have trained this convolutional neural network on the concatenated intensity phase image dataset for training and validation sets, where I have taken the loss curve on the training and validation set. I have taken loss as mean squared error. I have trained the CNN for 50 epochs. You can see here, the margin between the training error and validation error is small. So the convolutional neural network is correctly converging. Similarly, I have taken the metrics as mean squared error as well as mean absolute error. The training error is also decreasing, and the margin between training mean squared error, validation mean squared error is also less. This is the graph for mean absolute error. Next, I have calculated the evaluation metrics for the convolutional neural network on both test and validation sets, where I have taken the metrics as mean absolute error. R square score is used to measure the performance of the binary regression task. Explained variance regression score. If these two scores are approaching towards 1, then it has got good regression performance. If it is approaching 0, then it is having constant regression performance. If it is having a negative value, it means it is having a poor regression performance. So I have calculated the evaluation metrics on the test and validation sets. You can see here for the test set, I am getting 73% and 83%. For the validation set, I have got 25% and 30%. Next, I have calculated the evaluation metrics not only on the convolutional neural network. I have compared this regression task with several machine learning regressors. In the scikit-learn, we have several machine learning models: k-nearest neighbor, support vector machine, multi-layer perceptron, decision tree, ADA boost, random forest, extra trees, gradient boosting, histogram gradient boosting, stochastic gradient descent regressors. And I have calculated the R square score and EV regression score on both deep learning as well as machine learning regressors. You can see here 0.73 for CNN is more compared to other machine learning regressors, and 0.83 is more for CNN compared to other machine learning regressors. So I can conclude that convolutional neural network is having very good binary regression performance for this concatenated intensity phase image data set compared to other regressors. So this is my work. Thank you for providing me to present my research work.
Congratulations to most interesting presentation.
Thank you very much, madam.
I would like really to ask myself as a doctor, how can I use this deep learning?
Madam, deep learning Even I am from electronics branch. We can learn Python programming, madam. So through Python, we can learn neural networks. So we have to implement neural networks in TensorFlow. I have used a software called Google Collaboratory. So through Google Drive, Google Collaboratory, we can establish or construct a neural network, and we can modify the model, and we can generate the results.
And if I'm not, anybody can use Python and Google collaborating?
Anybody can use Python and Google Colab. I am from electronics background. I didn't had any idea about Python. Python is a very basic, simple programming language. Even a very intermediate person can understand.
Wonderful. And